So I'd like to take this opportunity to thank Dr. Brady West for coming here. Dr. West is a research professor in the Survey Research Center at the Institute for Social Research at the University of Michigan. He's an elected fellow of the American Statistical Association. He has first authored or co-authored 195 peer-reviewed publications in 8 books in the areas of survey statistics, survey methodology, applied statistics, and public health. He's also a co-author of the book Applied Survey Data Analysis, the second edition with Stephen Herrega and Patricia Berglund. His current research interest includes selection bias in surveys and analytic tools for the analysis of complex, longitudinal, and clustered data sets. And today he will be giving us a talk entitled Appropriate Design-Based Analysis of Complex Sample Survey Data, a topic that will be of relevance to any of us who analyze large nationally representative surveys and even other types of surveys. So thank you, Dr. West. I appreciate it.
Great, thanks, Calvin. Thank you for the very nice introduction. So hopefully everybody online can see the slides. I have my email address up here on the first slide. So if you ever like to reach out and contact me, feel free. If you have questions after the seminar today, be happy to hear from you and I'm always up for collaboration. So just let me know if you'd be interested in working on something and be happy to hear from you again. So. Okay, right. So today we're going to be talking about appropriate approaches to what's called design-based analysis of complex sample survey data. So I'll start with just some general points about what we mean by complex sample survey data. We'll talk about the definition of design-based analysis. We'll discuss appropriate versus inappropriate analytic approaches for these kinds of data sets. I want to show some examples of what can go wrong if you don't perform analyses of these data correctly. So some case studies and analytic error. We're going to look at some examples from the national inpatient sample data, and I'll show you some Stata and SAS code that can be used to do these analyses, but there are procedures available in many different software packages like R and SPSS. So whatever you guys might have questions about, feel free to ask, and you can interrupt me during the seminar if you have questions. Just raise your hand or unmute yourself on Zoom, and I'll be happy to answer your questions. And in the slides, I've included some references, so additional papers and handbooks that you can look at for more details. So just to get started with what is complex sample survey data, many national survey data sets are collected from analytic units, could be people, could be businesses, could be establishments, that are randomly selected according to a stratified multi-stage sample design. So the sample design itself has very complex features. And the common feature of all these sample designs is that they're probability samples. So in the sample design, everybody has a known probability of being selected. Every unit has a known probability of being selected before the sample is actually selected. So everything I'm talking about today is an appropriate approach for probability samples, not non-probability samples. So nothing I'm talking about today applies to volunteer samples or convenience samples or snowball samples, quota samples, anything like that. We're talking strictly about probability samples generally on a large area or national scale. So what you learn about in introductory statistical methods courses, those techniques generally assume that the data that you're analyzing arrives from a simple random sample where you have a list of units and those units are randomly selected. It's a very simple selection mechanism, nothing more complex like stratified or multi-stage sample selection. In real world large scale samples, it's seldom true that simple random sampling is used, especially when we're selecting samples from geographically widespread populations. And we want to use probability sampling to try to make inference about larger populations. So so-called complex samples generally feature stratification, cluster sampling, and weighting of survey respondents. So those are 3 common features that generally need to be accounted for when you're sitting down to analyze one of these types of data sets. And any one of these features makes a sample complex relative to simple random sampling. So you could have a purely stratified sample, you could have a purely clustered sample, you could have a sample that's weighted for whatever reason. Any of the above features makes a sample complex. And again, the common feature is that we're talking exclusively about probability samples. Okay. So some of these key points, if you haven't heard about these terms before, these design features, with stratification, what you do is you allocate the sample that you want to select to different divisions of the population. So you divide a population into all possible known groups, You allocate a certain amount of your sample size to be selected from each of those divisions. And this design technique ensures that you're representing your population with respect to these different strata. So you're not giving yourself a chance of missing any of these strata in the sample selection. The nice thing statistically about stratification also is that it tends to decrease your sampling variance. So it makes your standard errors smaller. You have more precise estimates when you stratify by design. So if a sample has stratification by design, you actually hurt yourself if you don't account for that stratification when you do the analysis, because it gives you smaller standard errors in general. Cluster sampling is where you sample larger clusters of individual units. So these could be neighborhoods, they could be hospitals, they could be schools, and then you randomly select people within those units. And what cluster sampling does is it saves on costs of data collection, but because units within the same cluster tend to be correlated, cluster sampling has a tendency to increase sampling variance. So you have a cost variance trade-off. And again, you would need to account for cluster sampling because of its effect on increasing your standard errors. Weighting is generally done to account for unequal probability of selection. So you might oversample certain groups in your population, give individuals a higher probability of selection. You might be selecting unequal sized clusters like neighborhoods or establishments. And furthermore, there can be non-response. Not everybody will respond to the survey. So there are additional weighting adjustments to account for the fact that not everybody who's sampled actually responds. So the weights help to reduce bias due to these different sources of selection, but they can increase the variance in your estimates, your standard errors, if the weights are highly variable. So the people who produce these kinds of national data sets try to make those weights to have as the least variance possible while also reducing bias. The more variance that you have in your weights, the more your standard errors are going to go up. So that's on the data producers. That's not on you as an analyst. They have to give you weights that are less variable to make your estimates more precise. So if you want to make sound inferences about a target population of interest, you need to carefully account for all of these sample design features when you're analyzing one of these data sets. And that's what we're going to be talking about today. So what is meant by design-based analysis? Most statistical courses introduce what's called model-based analysis, where for a given variable in a given set of data, you write down a probability model, linear regression model, logistic regression model, whatever the case may be, for a variable of interest. You specify that model, you make sure it's well specified, all relevant predictors, and then all of your inference, when you're talking about the results of that kind of analysis about parameters that you're interested in, like means, regression coefficients, et cetera, all of that inference depends on the model that you specified. Okay, so if you misspecify a regression model of some type, your inferences about relationships of interest could definitely be affected. You assume a variable is normal when it's not, some kind of issue like that, that can have an effect on your inference. Design-based analysis, in contrast, all of the inference that you make is based on what's called a sampling distribution. So if you had selected the same kind of sample over and over and over again, following the same design thousands and thousands of times, and you computed your estimate of interest, whatever it is, for each of those hypothetical samples, you would get a distribution of estimates. Not every estimate is going to be the same because there's sampling variability, but you would get a distribution of estimates. In design-based analysis, your standard errors are based on the variability of that distribution. Now, clearly you don't actually select thousands and thousands of samples in practice. You just get one chance because sampling is very, very expensive. But design-based analysis, the math underlying it, gives you the ability to estimate the standard error of that distribution based on one sample. That's one of the more beautiful statistical advances in all the 20th century, was the ability to make inference about a population just based on one probability sample. So we can estimate the features of that sampling distribution based on one sample. And an unbiased estimate when using your weights for estimation just means that that sampling distribution is going to be centered on the true population parameter. So failure to use weights in estimation may shift that sampling distribution away from whatever your true parameter of interest is. You want all those hypothetical estimates to be centered on whatever the true population parameter is. So with design-based analysis, you estimate the parameters of interest based on your sample, and you estimate the variability of those parameters or your standard errors with respect to the sample design, not with respect to the underlying models that you might be specifying. That's the key difference here. So all of your inference is governed by that random sampling process, the probabilities of selection, the weights, the stratification, the cluster sampling. That's what drives all your inference. You're talking about design-based analysis. And this is the best approach to make inference about finite populations. You can choose to take model-based approaches with survey data. There's nothing wrong with that. But it's all on you as the analyst if you're specifying the right model. And if that sample design information is relevant for whatever analysis you're doing, you ignore it, your model-based analysis can really go haywire. So design-based analysis at least gives you protection in the way that you account for the sample design features so that your estimation is unbiased with respect to the sample design. Okay. So that's going to be our focus today. So design-based analysis focuses your inference on a well-defined and finite target population. That's another key distinction. With model-based analysis, we assume some kind of infinite data generating mechanism, mainly our model of interest. We make inference with respect to that model. With design-based analysis, there's a finite target population in mind. Everybody in this building right now, for example, that could be our finite target population. And we want to make statements about that finite target population. Okay, that's a key difference here. All right, so again, with model-based analysis, all the inference is based on the specified probability model, and there's no concept or notion of a finite population. You're talking about some kind of infinite data generating process. So again, if your model is well specified and finite population inference is not critical, model-based analysis can be great. If you do a good job of specifying your model, it can be more efficient than design-based analysis. It can be more powerful than design-based analysis. But it's 100% on you as an analyst to make sure that you get the model right. With design-based analysis, we have some protection where as long as we're accounting for these sample design features, we have unbiased estimates. That's the key thing with respect to the sample design, right? So a nice kind of oldie but goodie paper on this distinction between model-based and design-based analysis is this paper by Hansen et al. 1983. It's a very readable paper that talks about these key distinctions between model-based and design-based analysis. And again, the references are at the end of the slides here, so you can take a look at that paper. You can easily download it from JSTOR at this point. Okay, so appropriate design-based approaches now that we've defined that concept. So how do we ensure that our estimates are unbiased, our standard errors are unbiased with respect to the sample design and the finite population of interest? First of all, we would use the final survey weights that you see in a data set for estimation, especially if those weights shift your estimates of interest substantially relative to the shift in the standard errors that they may introduce. Okay? So again, weighting has the risk of potentially increasing your standard errors, but those weights are ultimately designed to reduce bias in your estimates due to these different sources of selection. So it's always a good idea to start by evaluating your weighted estimates. Okay, and you can compare those to your unweighted estimates. There are techniques for doing that, but you want to see what kind of impact your weights have on your estimates. We're going to see that in our examples that are coming up here. So that's the first point, is think about the weights and their role in the actual point estimates that you're computing. Second step, you want to account for the effects on the sampling variance of weighting, stratification, and cluster sampling via various specialized techniques that have been designed to estimate the variance of that sampling distribution. Again, the fact that we can do that based on one sample. And so there are different techniques that have been developed to do this. The default in most software for variance estimation is Taylor series linearization. This is generally the default procedure that are going to be available in various software procedures for survey data analysis. An alternative is what's called replication or resampling techniques. This is the jackknife, balanced repeated replication, and bootstrapping. These are all techniques that can also be used to estimate variances. Some data producers do not want to give you stratification and cluster sampling information in the data set, and that's necessary to implement Taylor series linearization. What some data producers will do is instead give you so-called replicate weights. So you might see a data set with 100 additional weights added to it. These are typically weights that are designed to implement jackknifing, balanced repeated replication, or bootstrapping. And it's very easy to specify those replicate weights in the software. What that does is data producers can give you those replicate weights, which encode the sample design information, and then they don't have to release the stratum and cluster information. So it's a form of disclosure risk protection. And data producers often like to do that instead of giving you codes representing the strata and the cluster. So a lot of this involves taking a look at your data set first and seeing what's in there to reflect the sample design that was actually used.
Dr. West, these actually, whether you use design-based, the kind of the default design-based variance estimates versus replication weight.
Yep.
Do they typically give you the same result?
Yeah, they're typically very, very close. So an interesting thing in this area is that with large enough samples, Taylor series linearization estimates, which are based on calculus really to incorporate all the features, and replication estimates, they converge to the same value, large enough samples. Jackknifing, bootstrapping, it's an algorithm. Taylor series linearization, it's mathematical. And what's really interesting is that as long as you account for those sample design features, they both converge to the same values with a large enough sample. So you can go either way, and that's why some data producers say, well, I'm just going to give you the replicate weights, and I don't want to put my survey respondents at risk by releasing their stratum and cluster codes. Works equally well. So then once you have the point estimates, the weighted point estimates, and the design adjusted variance estimates, you generate confidence intervals for your parameters of interest with appropriate degrees of freedom based on the sample design. So this is another key difference. Generally, the degrees of freedom for your test statistics are not going to be based on something like the sample size -1 or the sample size minus the number of parameters going to be that are estimated. The degrees of freedom are based on the information that you use to estimate the sampling variance. So that's all driven by the clusters and the strata. So your degrees of freedom are going to be determined by how many clusters are in the sample and how many strata are in the sample. So oftentimes the degrees of freedom for statistical testing are going to be much, much lower than they are in model-based approaches because of what's used to actually estimate the variances. And most software generally will compute the degrees of freedom as the total number of clusters minus the total number of strata. So when you think about confidence intervals, that critical T value for say a 95% confidence interval, you often hear that it's like 1.96 or 1.965. With these approaches, it might be 2.1 or 2.2. We have fewer degrees of freedom that were for the variance estimation because of these sample design features. That's another key distinction here. But again, the software will take care of all that for you. It's not something that you need to worry about. So inappropriate approaches, in contrast, if you're dealing with one of these kinds of data sets, so do not ignore the weights entirely. This is especially true if the final survey weights in your data set are correlated with the variables of interest that you're analyzing and you really wish to make inference about some type of finite population. It's a bad idea to just ignore those weights entirely. I know some fields like economics tend to say, I only care about model-based inference. I don't care about your stupid survey weights. I'm going to ignore them, or I might include them as a covariate in my regression model. It can really go haywire, especially if you're focused on descriptive estimation of a finite population. So it's always a good idea to start by evaluating those weights in your weighted estimates. Do not ignore the stratification, the cluster sampling when estimating sampling variance. Again, some form of information about these design features is usually provided in public use survey data sets, whether it's the stratum and the cluster codes for linearization or replicate weights for one of the replication techniques. You'll see those variables provided in public use data sets, and you can input them to the software to make sure that you're getting the sampling variance right. Don't consider model-based approaches that completely ignore the complex sample design features. So again, I have no issue with model-based approaches. I use them all the time. Just make sure that somehow your model specification is accounting for these design features that could have an impact on your estimates. Just don't ignore them entirely. Okay? And I say the example here. So if you're fitting a model, say, to a clustered data set coming from one of these samples, maybe use random cluster effects to account for within cluster correlations, right? That would be a model-based approach to accounting for these sampling features, fit a multi-level model or something like that. And then do not use software procedures that do not process the complex sample design features correctly. I cannot tell you how many horror stories I've seen over the years. For example, when somebody uses the base SPSS software and they input final survey weights as case weights in the base SPSS software. And SPSS, for example, if a weight is less than 0.5, which is possible, given a weighting procedure, SPSS will drop all those weights because it's looking for frequency weights, and it's going to round those weights down to 0. And somebody with a weight of 0, guess what? They get thrown out of an analysis. And people come to me and say, why am I losing 1,000 cases? Because you're using SPSS and you're not using the appropriate software. Okay. So that definitely make sure that you're using specialized software that can handle this design information correctly. So what can go wrong if you don't follow this guidance? A failure to conduct these kinds of appropriate analyses can lead to erroneous conclusions about your population, incorrect inferences, point estimates that are shifted away from what they really should be, standard errors that are too small compared to what sample design was actually used. And if we consider the larger total survey error framework, which talks about all the sources of error that can affect survey estimates, an important source of error is analytic error. So even if everything goes right with the data collection, you do the sample design, you adjust for non-response, you process the data correctly, everything's great about the data until it gets in the hand of the analyst, and the analyst screws up the analysis, all that investment to make sure that you have high quality survey data could go right out the door. And so recent years have said, as part of the total survey error framework, we need to think about the role that analytic error plays in producing erroneous survey estimates. So the most common problem is that well-meaning secondary analysts without training in this kind of an analytic approach, they apply standard methods that they've used in other analyses to these complex sample survey data sets, and they write papers that could be prone to these erroneous inferences. That's really the common issue that we try to prevent with this kind of training. So again, what is meant by analytic error here? So if secondary analysts of survey data ignore these essential features of complex sample designs and analyses, again, whether you take a design-based approach or a model-based approach, inferences could be biased or erroneous. So the weights generally ensure unbiased estimation of your parameters with respect to the sample design. The stratum codes are designed to increase the efficiency of your estimates. Stratification helps to make your estimates more precise. Cluster codes generally capture losses in efficiency due to the need to save money and select cluster samples. So we want to account for all these pieces of information. And a failure to account for these features can negate the substantial resources that are dedicating to minimizing these other sources of error for any given survey. Survey data collection is very expensive. And it turns out that analytic error can be one of the bigger players in erroneous survey estimates relative to what data sets are actually produced. So analytic error has become a focus of research in recent years. Tom Smith, in a 2011 paper, again, also at the end of the slides, was the first to really say that analytic error should be an important component of the total survey error framework. In a book chapter in this book called Total Survey Error in Practice, I worked with some graduate students to review 100 peer-reviewed journal articles that were presenting secondary analyses of survey data. Most of these had a public health focus. And we found in this initial study that a failure to account for weights and complex sampling features and estimation is extremely common in these peer-reviewed journal articles. Again, because even the reviewers aren't aware of some of these issues. Okay. Furthermore, subpopulation analyses, where you want to analyze, say, older males or African-American females or whatever your subpopulation of interest might be, they're rarely performed correctly in design-based analyses. Again, I should add this to the do not slide, but a very common issue in design-based analysis. If you want to focus on a subpopulation, okay, don't delete the cases that you don't care about. Okay, process the entire sample and include an indicator in your data set. 1, 0, simple as that. These are the cases in my subpopulation. These are the cases I don't care about, but don't delete anybody. Have that 1, 0 variable in your data set, and then you provide to these design-based analysis procedures that 1, 0 variable as what's called a subpopulation variable. And what that means is that the procedures will process the entire data set, recognize all the sources of sampling variability, and incorporate that into your estimation, rather than thinking that the cases that you deleted were never there to begin with. The issue there is that you could have what's called a sampling 0 in one of your sampling clusters, where you didn't get any older males in this sampling cluster, but you could have by design. And if you just throw out that cluster because you deleted those cases, the software has no idea that it ever even existed.
And so your standard errors can be underestimated.
Practically speaking, I just want to make sure I understand what you're saying.
Yeah.
This is where SAS will yell at you if you're using proc survey freak,
Yeah.
and you use a where
Where
statement.
or a by or an if, right, right? Software reacts to it differently. I like what Stata does, honestly. Because if you use a subpopulation analysis and you throw out enough clusters where all of a sudden you can't really estimate sampling variance, Stata just doesn't give you standard errors. SAS kind of slaps you on the wrist and puts something in the log. Stata will just say, no standard error for you. And I like that approach better because it reminds you that there are better ways to do this. But the key point is just never delete cases that you don't care about.
So the where approach is incorrect.
Incorrect. Yeah.
In
In SAS, you would use domain. So I'm gonna come back to that. Yeah, domain is SAS's option for subpopulation analysis. Stata has a subpop modifier that you can use. The different software makes it easy to specify the domains. The key is that you do it. That you just don't, delete cases that you don't care about. Yep. Okay. So, of course, the natural question is, well, how big of a problem is analytic error? So how often does this happen and what are the implications? So really, what is the prevalence of this apparent analytic error in other peer-reviewed journal articles, conference presentations, book chapters, technical reports? Have there been trends across the decades in terms of prevalence of these errors? So are they becoming less common over time? Do journal-specific features dictate these error rates? So impact factors, having statisticians on the editorial boards, like how does that impact this? And then what are the implications of making these errors for estimation and inference? So I'm just going to present some selected results from work in this area. So we actually received an NSF grant back in 2015 to analyze data from the National Center for Science and Engineering Statistics. This is part of what was called the Science and Engineering Statistical Data System, basically large-scale national surveys to understand the workforce in the US and look at questions related to STEM education. So we selected a stratified sample of 150 research products. So this could have been peer-reviewed articles, conference presentations, technical reports, etc. Based on Google Scholar searches, we organized these by decade, again, to get a sense of trends and what's happening here. And we sampled 50 articles that presented secondary analyses of each of 3 main SEStat surveys, all of which have complex samples. So you can see the names here: NSCG, the Survey of Doctorate Recipients, and then the National Survey of Recent College Graduates. So these are just examples of these large national survey data sets. We coded these 150 articles on all these following points. So this, again, took a long time to go through the articles and code this information. But the most important things for the presentation today, we want to see, did the analysis account for weighting? Did the analysis account for these design features and variance estimation? Did the authors perform appropriate subpopulation analyses? And then for journal articles in our sample, what was the impact factor of the journal? Were there statisticians on the editorial board? And were there guidelines for survey data analysis on the website? Next, we looked at the implications of making these errors by downloading the exact same data sets and then implementing the kind of analysis that was suggested by the authors of these papers to see what would happen to the different estimates. So we downloaded the data sets. We obtained the replicate weights, which is what NCSES provides for variance estimation. And we reviewed the sampled articles and worked with the NCSES staff to identify key descriptive estimates and regression models that would be of substantive interest to NCSES users. We performed 3 types of analyses for both descriptive and regression parameters. One that fully accounted for the complex sampling features, what I'm today calling the appropriate analysis. One that accounted for the weights only, using Taylor series linearization for variance estimation. This is another very common misconception, is that if you account for the weights in estimation, everything will be taken care of. And that's not the case, because doing that ignores the stratification, the cluster sample. Those other key players in the variance estimation. And then just the naive approach to ignore the complex sampling features entirely in the analysis. And then we looked at ratios of the variance estimates to get a sense of these misspecification effects that were arising from ignoring these key sampling features in the analyses. So first of all, here's the meta-analysis of our review of those 150 sampled articles. We had to throw out 5 of them for various reasons, didn't have enough information. But the key points across the different surveys are in that last column, the overall sample. Accounting for sampling weights and analysis, half.
Accounted for complex sampling and variance estimation, less than 10%. Okay, using a design-based approach versus a model-based approach, a little more than half. Using appropriate subpopulation estimation, a little over 10%. Okay, describing results with respect to the population versus saying, here's what my sample says. Articles generally did a pretty good job at that. But the other numbers are staggering. If you extend this to larger scale, more than 150 sampled articles. This is the trend question. So again, we broke up these articles by decade. You can see less than 2001 to 2010, greater than 2010. Basic message is no matter what aspect of the analysis that you're looking at, whether or not weights were used, whether or not variance estimation was done correctly, using correct subpopulation approaches, it's flat. So this problem is not changing, it's not getting better over time. So again, it's very important for people to recognize the importance of doing these things correctly. So there was no variance in apparent error rates depending on the type of research product, whether it was a journal article, a conference presentation. In fact, we found that journal articles were the least likely to use appropriate variance estimation of all the different kinds of products that we looked at. Having statisticians on the editorial board did increase the probability of using appropriate methods. That was a good thing. Model-based approaches were particularly likely to ignore design features. There were generally vague references to robust standard errors without clarification. You have a question?
Yeah, thanks. This is fascinating. My question is, I know that you decided to include whether or not there was a statistician on the editorial board. Most editorial boards don't necessarily function as a, a filter for anything other than a discussion once a year of, general subscription rates. My question though is what, some journals have kind of a required statistical review.
That's what I mean.
So that's different than a statistician on the editorial.
Well, so for example, I'm a statistician on the editorial board of a journal called Field Methods. And when they want me to review if an analysis has been done correctly, if there's debate among the reviewers, they don't know how to evaluate it, they ask me to review that paper.
So that's one model of that. But some journals have a statistician on their staff whom they pay to review, independently journal articles. But that wasn't one of the features
We
here.
broadly coded it that way. So they looked at the editorial boards and saw if there were dedicated statisticians there. So they couldn't follow up with these individual journals and say, exactly what model is used for that statistician to become engaged. We just wanted to see if that was a built-in feature of the editorial board, however it was implemented.
Yeah. I think some of our journals just put a statistician on there because it looks good. I'll just be very candid.
Yeah, so that could perfectly be the case, but in that general coding, we did see some evidence of that being beneficial. And just to kind of foreshadow, we have a new paper coming out that's presenting like a Prisma set of standards for design-based analysis that we're trying to spread as widely as possible to make that just as common as Consort, as Prisma, things like that. We have a new article coming out soon that's laying out that kind of guideline for journals. So
Where did you publish this meta-analysis?
this was in PLOS One.
So you can download it online, no problem. It's in the references too.
I think it's great. I just want to say,
Okay.
hats off to you.
Thanks, I appreciate it.
But one of the things we found is that the journals almost never provide guidance with regard to appropriate secondary analysis of survey data, which you would think it would be just important if the journal is going to accept these kinds of articles, but it's never there. Like the journals will say, oh, we want to see response rates, we want to see missing data, we want to see sample sizes, but you'd think this is more important. It's just never there. So it's interesting.
We have a question from the chat.
Oh, yeah.
From Kevin Bukowski. Is the impact of improperly specified weights or ignoring them to understate the standard errors, which leads to confidence intervals being too narrow?
No, ignoring weights, the biggest impact would be on the estimates themselves, right? If those estimates are informative about what you're trying to, or if the weights are informative about what you're trying to estimate and you ignore them in the analysis, you could have severely biased point estimates, which is what drives a lot of what our conversation is about.
And I'll show some examples of that in a second. So of course, we talk about these apparent errors and you say, well, what's the big deal? Who cares? Right? What are the implications? What actually happens if you make these errors? Right? So what we did in our analyses is We looked at 8 categorical variables in the 2010 survey of doctorate recipients. And we found that inferences related to simple descriptive estimates in the population, means and proportions, would change for 5 of the 8 variables. If the design features were ignored, you would arrive at a different inference about something as basic as a mean or a proportion if you ignore these design features. Current salary, race, ethnicity, attending professional meetings in the past year, your major field of study, your labor force status, different inference. And if you look at 10 continuous and categorical variables in the 2010 National Survey of College Graduates, 9 of them changed. Right? So in this case, the weights are very informative about the
Say
measures.
substantial, sorry, when you
I'm going to show that in a second. I'm going to show what I mean by substantial.
your biggest
So-
fan here.
So here is what answering that question. This is an example from the 2010 National Survey of College Graduates. Very common indicator for what's happening with STEM education. Is your primary job in science and engineering? Okay. If we fully account for the complex sampling features, you get about 30% of jobs. Okay, in the standard error. If you only account for the final weights, you get the point estimate right, which is good, but you can see the standard error is a little bit higher than it should be because we're not getting any of the gains in efficiency from stratification. We're ignoring that feature of the sample design. If, however, you completely ignore the weights in that estimation, what happens? You might be writing a paper that says more than half of people have STEM degrees. And all of a sudden you're trying to light fires and people are like, wow, that can't be actually happening. Is that right? What's all the concern about? Because they ignore the weights. Now, why are the weights so informative? Because this particular study, NSCG, oversampled people likely to be in science and engineering. It's very simple.
Wow.
You need to account for them to make appropriate population estimates. And you can replicate this analysis yourself. I'm not just making these numbers up. You can download the data and do that analysis to see what happens. Okay? And it's because the weights were highly correlated with a lot of these key measures. It's not just for descriptive estimates. In a logistic regression model that we fitted to a binary indicator of having an annual salary of greater than 150,000, looking at the interaction between a major degree and race ethnicity, another very common research question, would change. Fully accounting for the sampling features, there's a significant interaction that we need to worry about. Okay, where race ethnicity moderates the relationship of degree with having a higher salary. If you only use the weights in estimation, it's like nothing's happening. Gains due to stratification. If you do a wall test, ignoring all these design features, looks like nothing's happening. So you might miss an otherwise interesting finding by ignoring the design features. Same thing applies to regression. Okay, so this just kind of summarizes everything we just went through. For the sake of time, I'm not going to go through all this in detail, but meta-analysis suggests it's a problem. There are severe implications. There can be severe implications of failing to account for these design features. Not always, but there can be. And related work looked at establishment survey data. So not human beings, but establishments, same issues. Nothing changes in surveys of establishments. Okay, same basic statistical issues. So there's a paper there in 2018 that we looked at for that. So this wasn't just me tooting my horn. There's been other researchers who have done the exact same kind of stuff in a medical area. This paper by CHEAR et al. in 2017, they looked at 120 out of 1,082 published studies that used the national inpatient sample, which I'll show some examples from. 79 of the 120 studies, more than 2/3, did not account for these features. It's not just me. It's not just ISR. Other people are finding the exact same thing in different sets of research. So and these are all peer-reviewed journal articles. They didn't look at conference presentations. They didn't look at technical reports. This is all peer-reviewed journal articles. So more than 2/3 of these studies are at risk of reporting erroneous inferences. Again, they might get lucky. The weights might have nothing to do with their key variables, fine and good, but they're at risk of reporting erroneous inferences. That's the point. Okay. So let's look at some examples of this kind of appropriate approach using that national inpatient sample. Starting with the 2011 data set here, I just picked out some random dependent variables. So this indicator of died So there was an in-hospital death during the admission, 0 otherwise. And then a continuous measure of total charges for hospitalization. See, those were our 2 variables of interest. I grabbed a series of covariates of different types. You know, are you a female? Was this an elective admission? Age, length of stay, primary payer, and then race. And we're going to consider descriptive analyses for all these variables and regression models for the 2 dependent variables. So step 1 in these kinds of appropriate analyses, always start by reading the documentation. Don't just dive into the analysis. Read the documentation for your data set and identify these key variables that capture the complex sampling features. Okay, you can always talk to somebody and ask for help about what the appropriate variables are, but the best source is just to read the documentation, because usually there will be an entire section dedicated to, if you are analyzing these data, here's how you account for the sampling features. That's the ideal documentation. It's not always that easy, but it's there somewhere, okay? In this case, the final survey weights were in a variable called DISC weight. The sampling strata were in a variable called NIS stratum. And the sampling clusters, which were hospitals, were in a variable called hosp-ID. And these were the 3 variables that we need to specify to implement Taylor series linearization as part of our analysis and to get the right kind of weighted estimates. Oops, sorry. So, first kind of approach that you might take, again, naively, is to ignore the design features entirely. Okay, so you say, I don't care about any of this information. I'm going to use the methods that I know and love, and that's it. Okay, so in SAS, I might just use proc-free, get some tables. I might use proc-means, look at the variables of interest, total charges, age, and length of stay. In Stata, I might just use the prop command and then the mean command for my basic variables, just to get these basic descriptive statistics. Okay. Possible approach number 2 is I say, oh, the weights are important. I'm going to use those for analysis, but I'm going to ignore the other design features. Okay. So now I'm using proc survey freak, and proc survey means those are the appropriate procedures for design-based analysis of survey data, but I'm only doing part of it correctly in this code. I'm specifying the weight variable correctly in these survey procedures, but I'm failing to specify the stratum codes and the cluster codes that are also critical for variance estimation. In Stata, what you do is you set your design variables first with survey set. In that survey set command, I'm only declaring the probability weight, the DISC weight. I'm not also declaring the stratum and the cluster codes. And then you can see the way that Stata works. What you do with design-based analysis, you just modify each of your analysis commands by adding SVY : in front. That's how you implement appropriate design-based analysis in Stata. So it's mindlessly simple to do. The key thing is just to do it. That's what's really staggering about all this research and everything, is that the software nowadays has made it very easy to do the right thing. But for reasons A, B, or C, people still aren't doing it. So again, this is just specifying the weights. Now, here's how we do the appropriate analysis, fully accounting for all of the complex sample design features. In survey freak and survey means, not only do I add the weights, but I add the cluster codes and I add the stratum codes. Okay, I fully specify all those design features that the NIS provided, okay, both for survey freak and for survey means. In Stata, in my survey set command, I specify the cluster codes first. I have my weight, and then after a comma, I indicate my strata, the codes representing the strata. So fully specifying all those design features. The actual analysis commands are still the same. I just have a different set of design features that are specified, that's all. So this was what I would call the appropriate approach. So here's a comparison of estimates based on those 3 approaches. These are just descriptive estimates. So approach 1, ignore, approach 2, weights only, and then approach 3, fully accounting. What you see in this example with the NIS is that the weights are not that informative about these 2 variables. So see, the point estimates themselves don't change. There were only deaths about 2% of the time. Doesn't matter how you look at it, okay? What does change is the standard errors. Notice what happens to those standard errors in terms of inflation as you fully account for all the design features. The key thing here was the cluster sample due to the hospitals. That's where we saw an increase in the standard errors due to the cluster sampling. So unlike the NCSES example, in this case, there were minimal changes in estimates because the weights were not correlated with these indicators, but there were changes in the standard errors. Okay. Here's means. So not just looking at percentages. Same basic issue in the point estimates here, means very similar, accounting for the weights. Standard errors, look what happens to the standard error of total charges. How far we would be understating the standard error, not fully accounting for the design features if we had ignored the stratification and cluster sample. Okay, we're severely overstating the precision of that estimate, ignoring that important feature of the sample design. Okay, another key point, don't forget about subpopulations. As I mentioned, don't simply delete cases that do not belong to the subpopulation. Instead, you can use these simple additions to the analysis commands to specify this binary indicator of who's in your subpopulation and who's not. So in Stata, you can just add the subpop option before the colon. And in SAS, you add a line that says domain and then the name of your indicator variable. Okay, so again, it's simple to account for this. The key is that you just start by creating that indicator variable in your full data set first, and then specifying it to the procedures using one of these techniques in SAS or Stata. And different software handles this in different ways. The key thing is just to define that binary indicator first. Okay. What about regression? So here's approach number one in regression analysis. So we might use survey logistics, survey reg, or logit or reg in Stata, where you don't specify any of the design features. No weight, no stratum codes, no cluster codes, okay? Just the basic analysis, assuming simple random sampling. This is what the syntax would look like. Approach two, now we're accounting for the weights and fitting the regression model. So you can see I'm specifying a P weight in Stata, and I'm adding the weight statement to the survey procedures within SAS, just like we did before, to fit the models. And then approach three, fully accounting for all those design features, the weight statement, the cluster statement, and the stratum statement. And then in survey set and Stata, I'm again specifying each of those three design codes to make sure that I'm fully accounting for all these features, okay? So here are the estimated regression coefficients in this linear regression analysis. So approach one, ignoring the weights, approach two, accounting for the weights only, and then approach three, fully accounting for all the design features, same pattern that we saw earlier. The weights were not informative about these regression estimates, but we do see changes in the standard errors, and even those are relatively slight. So these design features might be less informative about regression coefficients than they would be about descriptive parameters. So if you do a good job of specifying your models, the sample design might not play a huge role in the estimates. That happens a lot with regression. Yep.
Can I ask a really practical question?
Yeah.
So for like the NIS or the NRD, like any of the HCUP databases,
Yeah.
which are super large sets, and in
Yeah.
you know, in Stata you have to like it uses your memory to upload
Yeah.
these big samples. So often I'll subset to like patients under 18,
Right.
right? Does that, by subsetting up front, does that mess up your subgroup analysis?
Yeah, that's the issue. So even though it's a huge database, you would still want to.
Yeah. Yeah.
It's so intuitive.
Right, like, because it's like these things just won't.
So what I call it getting lucky sometimes.
Yeah.
So you might subset. And you might still have sample in all your clusters,
Yeah.
all your strata. You might not be at risk. The key problem arises when your subsetting results in a deletion of design information. So you delete an entire cluster or you delete an entire stratum. That's when it becomes a problem.
Okay.
So it's just you get it right either way by using the subpop option. Yes, it becomes a processing issue,
Mhm.
but if you just get into the habit of doing that by default, you'll never run into that problem.
Related to that, when we request data sets
Yep.
from IHPI,
Yeah.
we will often request, I want the
It's the same
DSP.
issue. Yeah.
So they don't give any different weighting if you're only.
Well,
requesting data.
that's another thing is that the weighting adjustments for a very specific subpopulation may need to be different from what was done for the full population. So that's a possibility. Typically, they try to develop weights that will accommodate as much of that as possible. But that's another perfect example of this subsetting approach is when you request a block of data. And doing that you might lose for the sampling clusters.
But they often only want us to get like the block of data that we're using, which is also really.
Well, but this is,
Yeah.
well, this-
Problematic.
normally if you're requesting stuff from IHPI though, you're requesting a convenient simple like market scan, which may come up with like they may come with post stratification weights to
Yeah.
make it. And so I feel like
That's the weights, right? That the issue is with sampling clusters,
Yeah.
especially for linearization, is that if that request, yeah, you might get the right kinds of adjusted weights. But if that request throws out
5 hospitals or whatever, you're gonna be understating your standard errors.
So I think for the H cup stuff that's available through IHPI,
Yeah.
the take home is just request for the entire thing.
Yeah, the whole
And then
thing,
create that indicator.
and then create that indicator, yeah.
I think is a good idea in general. Just
Yeah.
always request the full
But
data
this
set.
is-
In a situation where you can't do that, like they're not gonna give you the whole.
Yep.
They're just gonna give you your block, how do you account for this then?
Cross your fingers. The best check is when you get that cut, do a simple crosstab of the stratum and cluster codes. And if you see sample in all of those different cross classes, then you, like I said, got lucky. You didn't lose any strata, you didn't lose any clusters, everything looks good. It becomes a bigger issue if the cut that you want is a very specific subpopulation. Like Latino men over the age of 80 who have ever had cancer. Right? Then you're at significant risk of throwing out design features if you subset and don't use the subpop options correctly. So it's a good descriptive check to always look at that. It's tricky because again, you're at risk of severely understating your standard errors in that situation. And there you just might have to work with the data producer to try to get more information or something of that sort, or just acknowledge in your analysis that these standard errors may be understated because important features of the design were left out in the request.
If there isn't purposeful sampling, but you have clustering by hospitals or by regions or something like that, I'm thinking of some prospective observational cohort where there wasn't a purposeful sampling, it was really recruiting all patients.
Convenience, yeah.
Yeah, it's a convenience sample. Do you have this issue?
No, because in those situations, again, this is all for probability sampling.
That's not.
In those situations, it's on you just to specify the right model for those data. So like I mentioned, if you have this clustering by hospital in a purely observational study, you might use random effects, or you might use GEE or something like that to account for that lack of independence.
Thank you.
That's right. Okay, so the point here, again, with these regression examples, weights are not informative, standard errors do change somewhat, but the weights don't play a huge role in the estimates of these regression coefficients, okay? So the weights were not informative, but again, this is not always going to be the case for every data set. And I just refer you to that extreme example in the NSCG case. So accounting for the strata and clusters does matter for inference, especially when forming confidence intervals. And with something like the NIS, your degrees of freedom for forming intervals are like 7 million, when in fact they should be 800. Accounting for the design features, so that's another really extreme difference, okay? Now, one just final comment about the NIS. Beginning in 2012, all the NIS microdata were self-weighting, which means that they came up with a design where there were not differential weights for different individuals. However, and I emphasize the however, that doesn't mean that you can simply, again, ignore the strata and the sampling clusters when estimate variance. Again, the weights don't tell the entire story. So even if it's self-weighting and you don't have to worry about weights, in your analysis, you should still account for those features of the sample design. That's a critical thing. So here's what can happen in that situation, okay? So using 2012 data, which again are self-weighting, in approach 1, I ignored the strata and the clusters. In approach 2, I accounted for the strata and the clusters. Again, big samples, okay? So no concern about sample size. You see the estimated means because weights aren't a critical issue. But look at the standard errors again. If I failed to account for the strata and the clusters, I'm severely understating the standard error. I'm saying that my estimates are way too precise given the sample design that was actually used. Okay, so same issue here.
There's another question from the chat, and I also want to recognize that we are a little bit over time.
Yeah,
So
sorry.
we're gonna cut, we'll end soon, but there's a question that says, how do you approach survey products that include a post-stratification weight that is supposed to account for the strata, where they don't provide a strata variable?
Yeah, see that post-stratification weights can account for stratification after the fact. That's why it's called post. But that's strictly designed for adjusting the weights to make sure that your point estimates are in some sense unbiased. That does not have anything at all to do with the variance estimation. So you have 1/2 of the problem right in that case. If they don't provide stratum codes or cluster codes for variance estimation, that's a problem on the part of the data producer. they have to give you some means of adjusting your standard errors to account for the effects that you see here. Otherwise, they're basically forcing you to report estimates that are way too small for the standard errors. Some data producers will give you what are called design effects, which are kind of like variance inflation factors that you can multiply your standard errors or your variances by to get them in the right shape. But that requires working with them to make sure you track down that information. Otherwise, you're at risk of this issue here. Okay, so sorry for going a little bit over, but these were really good questions. So thanks people for raising them. Here are the references that I was referring to throughout the presentation. So some of these are book chapters or books. Some of them are papers. I'm happy to share any of the papers, but these are all very good references that provide more information about the issues that I've been discussing today. So, and I'm happy to provide others if people would like to do more reading in any of these areas. But I think the PLOS One paper is a good primer about the overall issues here. If you want to share that with colleagues or take a look at that in particular among all these different options. And again, if you have any comments or questions, or you want to talk about these issues any further with me for some of your research or whatever the case may be, just shoot me an email at bwest@umich.edu. Okay.
Thank you so much.
So thanks everybody. Yeah, thanks for the invitation. Yeah, if there are any chat questions, I'm happy to answer those. So.
Got the survey link up there. Yeah.
Are we good on, were there other chat questions?
No, I think we got all the questions.
Okay.
So thank you. I think I was just trying to get the survey link to show up so that we can do our evaluations, but thank you so much.
Great. Yeah, thanks for the invitation. Appreciate it. Yeah, hope it was helpful.